Yeah, thanks for organizing this forum, and it's an honor to be here. Today, I'm going to represent our recent work on using neural work quantum Monte Carlo on strongly correlated topological flat bands, which is a joint work by Peking University and by Dan Seed. Okay, I'll start with an introduction to strongly correlated topological states. The first example to quantum Hall effect is the integer quantum Hall states, where the non-interaction electrons form lambda levels under magnetic field. And later, fractional quantum Hall effect was found as insulating state at fractional fillings of lambda levels. And this state is highly strongly correlated in nature and cannot be understood with simple single particle picture. And Laughlin and Chen proposed a genius wave function into this problem, the composite fermion theory. And in Murray systems, there's a counterpart of the FQHE effect. There could be a sequence of topologically non-trivial flat bands in Murray systems, and this is similar to lambda levels in electron gas and may lead to the quantum anomalous Hall states. And strong electron correlation in this system may give rise to fractional Chen insulator. It was predicted first in 2011 by a series of papers and then confirmed by experiments. Okay, now we've discussed about two systems that is topologically non-trivial and there are flat bands. The electron gas on the magnetic field, the lambda level are perfectly flat and strong electron correlation gives rise to the fractional quantum Hall states. And another system is a Murray superlattice, where the band structure is flat and topologically non-trivial in nature. And strong correlation here gives rise to the fractional Chen insulator. Flat band here introduces the strong correlation, and the Coulomb interaction the Coulomb energy is way larger than simple body turn. And the single particle picture fails here, and the problem is exponentially hard. And current numerical methods face some problems here. The mean field methods like hydrofocal DFT, they fail for these strongly correlated systems. And fixed phase diffusion Monte Carlo, they relies on the child wave function for exact diagonalization. The high computational cost requires band cutoff. And for DMRG, it applies for the quasi 1D geometry only, and other geometries like torus or sphere, we also need them to understand the fractional quantum Hall states. And all in all, fractional quantum Hall states are hard to solve. Here, we use the neural network quantum Monte Carlo to solve this problem. And this is how NQMC work. We use a neural network ansatz to approximate the ground state wave function. As you can see, the electron degree of freedoms like coordinates, spins, they are all put into a neural network. And the network gives out the amplitude and phase of the wave function. As there are a great amount of parameters in the neural network, it gives a great flexibility, and we can approximate the ground state very accurately. After optimizing the parameters in neural network with unsupervised learning, it gives us accurate results for both energy and wave function. And this optimization follows the variational principle, which assures us that when the energy is lower, the wave function is better. Okay, neural network has been booming these years, and there are a lot of works to push forward the system size and the accuracy, and also the applicable system scales. Our team also made a lot of efforts in developing neural network wave function architectures and to extend the application of this method to various systems, including both real materials and model systems. Okay, and neural network has become highly accurate. It's its most important feature. Here's an example in hydrogen chain. As we can see, the neural network has reached a sub-millihartry accuracy and is comparable to the state-of-the-art methods like AFQMC. Okay, now we apply this highly accurate method to fractional quantum Hall effect. Laughlin and Jane has proposed this genius ansatz. However, as we can see, it is restricted to the lowest lambda level, and how can we go beyond the lowest lambda level and account higher lambda levels to? And for this purpose, we developed the deep Hall architecture. Here we consider electrons on a sphere, and the Hamiltonian is formed in continuous real space. The electron coordinates are fed into the neural network, where the electron correlation are encoded automatically with the network. And then the features are combined with the physical constraints. Here we use monopole harmonics to deal with the singularity and north and south pole of the sphere geometry. By combining physics into neural network, it can be fundamentally physical and more expressive. Okay. With this specifically designed architecture, the network has reached high accuracy. The left fig shows that the training process of the neural network. We can see as the neural network converges, it reaches lower energy than lowest lambda band exact diagonalization, and it's even more slightly better than fixed phase DMC. And also, neural network can capture some of the higher lambda level mixing. On the right figure, neural network, the orange line shows the ratio of electron number dwell on the lowest lambda level. And when the band mixing is stronger, the electrons on lowest lambda level decreases, and neural network automatically learn about it. Okay. Neural network can also provide us with physical insights. This figure shows the phase of wave function. Here, all but one electrons are fixed. When moving one electron around another, there is a non-trivial 6π phase gain for this loop, which is just the flux as predicted in Laughlin theory. Okay, and the wave function, the neural network also provides us information about excitation. Here is the density of quasi Hall and quasi electrons on a sphere, and the density is dependent on the polar angle. Okay, now we will show the neural network application in fractional quantum Hall effect. We now turn to fractional Chern insulators in Murray lattices without magnetic field. There are some questions in this field. On the left figure, ED predicts FCI state as the ground state for 1/3 filling, while in experiments, this 1/3 FCI is absent. So why are 1/3 FCI states missing in experiments, and what's the role of band mixing? And most importantly, we can ask, can neural network tell us more about FCI than existing methods? Here we focus on bilayer van der Waals materials like MOTE2. Here the Hamiltonian can be simplified into a 2x2 matrix where the dimension of 2 comes from the layer degree of freedom. And this Hamiltonian is somewhat similar to the spin orbital coupling form. And architectures of neural networks can be adjusted for this system feature. Here we show the structure of the neural network. Electron correlation is automatically encoded with a GNN here to reproduce spatial orbitals. And the layer degree of freedom are considered by using a spinner here. Here, Si is the pseudo spin, which is just the layer degree for freedom. And to deal with the periodic condition, we use a plane wave envelope, which is just EIKR. And finally, for anti-symmetry, we use a determinant at the end of the network. Okay. We now apply this network to MLT2. It captures some of the key features of fractional Chen insulators. On the left is the ground state energy at each momentum sector, that is the ground state for the ground state with a fixed total momentum. And we can see the ground state is threefold nearly degenerate and at exactly the K points predicted by theory. And this is a sign for FCI. On the middle figure, we show the ground state energy when inserting flux. The ground state is threefold nearly degenerate and with a gap to excited states. And when inserting magnetic flux, the ground states flows into one another with a periodic of 6 pi. That is also a feature for FCI. In figure C, we show the electron number distribution in first Brillouin zone, and the electron number distributed nearly uniform. So we can see now neural network is accurate enough for capturing FCI. Okay, now I'd like to make a comparison to ED. Neural network beats finite band ED for better scaling to system size and for higher accuracy. On the left figure, we can see that neural network has a cubic scaling to system size, which allows us to perform calculations in larger systems with lower size effect. And on the right figure, we can see that neural network quantum Monte Carlo provides an energy lower than ED. And as the variational principles assures us, the lower the energy is, the better the wave function. Okay, and neural network may provide us with physical insights. We can see NNQMC has predicted the charge density wave to be the ground state, while ED predict a FCI state. And so FCI is not stable for 1/3 filling when considering more bands. On the right figure, we show the electron occupation on each type binding bands. Here we can see a decent amount of electrons dwell on higher bands, and band mixing is important in this problem. Okay, here's the take-home message. Neural network is a powerful tool for strongly correlated states. It is highly accurate with favorable scaling, and it may bring us new physical insights as a result. And thanks for listening. So fix the DMC. You mean here?
I meant like there was this energy comparison with Monte, like those one not on ED and
Yeah.
and so that you use this
Just from literature.
Two questions. It's nice to see that you can beat ED when ED is limited to that one band projection.
Yeah.
But do you also have a precise comparison of your energies with, for the same projected model between the neural network and ED when it's feasible? And my second question is, can you give a bit more detail about the architecture of the network and how the wave function is actually constructed? The backflow, how is it done?
Oh, okay. For the first question, yeah, we are actually better than 3-band ED, and we cannot constrain the neural network to finite bands. We are in real space, and just all bands will go in. Yeah, because we use a real space continuous Hamiltonian for neural network. Yeah. Let me see. For the second question, we use a architecture that is similar to FermiNet or Deep Solid. Here, the electron positions forms one electron and 2 electron flows, which is just the coordinate or the relative coordinates. And here we use GNN, which is a graph neural network that combines the information in 2 electron flows into the 1 electron flow. And so that the electron correlation is encoded. Okay.
Could you elaborate a little bit how you mix spatial optical and spinor information?
Spatial?
After GNN?
Yeah. After GNN, the spinor orbitals, they're just multiplied to the spatial orbitals directly. And here we use a continuous representation for the pseudospin as shown on the bottom left. It's a superposition of top and bottom layer degree of freedom. After that, the periodical condition, the plane wave, just the plane wave was multiplied into the orbitals we get before. Okay. Mm-hmm.
I have 2 questions. Yeah. So traditionally when we talk about SDI, what's it called is dimension, like the hypothetical spectrum that is also very important. Why is there a problem with the real space representation to calculate that? That's the first question. The second question is like, so when we talk about hypercorrelate asymmetry between 1/3 and 2/3, the non-uniform curvature or like the geometry also destroy that. So is it more important for the geometry distortion or the effect? That's the
Yeah. For the first question, because we consider the homobilayer MLT from the real materials, and so the Hamiltonian is naturally formed in real space, continuous real space form, and so we use the continuous space. Is that okay?
So it's not possible to compute
No, it's hard to get the entanglement spectrum. Yeah.
The second question
And
is geometry distortion.
yeah. For the second, I'm not quite sure about the second question. And because the, yeah. Yeah, sorry, I can't answer this.
So let's send the speaker again.
Okay.